Okay. Today, we're going to start with chapter 4, which is reactions in aqueous solution. And so there are, I would say, four primary topics in this chapter. The first is what we call precipitation reactions. The second one is acid-base reactions. The third one is redox reactions. And then the last thing is some calculations using molarity. So let's start off today by talking about the precipitation reactions. And precipitation reactions are typically reactions that do occur in water. So when a reaction occurs in water, we tend to call that an aqueous solution. Water is the solvent. So let's remind ourselves a little bit about the idea of solvents and solutes and such. So we all have this sort of idea, this understanding that if you take water and you put it into a coffee cup or into some kind of container, so you have water in here, that some things dissolve in the water, right? Some things dissolve in the water and other things don't. So for example, if you take a little penny and you drop that in, it just falls down to the bottom, right? It does not dissolve. So we would say that the penny is, is insoluble in water. That means it does not dissolve in the water, right? And typically most metals do not, most elements actually, most elements do not dissolve in water. There are a couple that you can kind of get to dissolve. Some metals will actually react with the water and then they dissolve. But for the most part, most elements are just insoluble in water. They don't dissolve, okay? And then you have these things which we call ionic compounds. And ionic compounds are interesting. Ionic compounds, we'll talk more about this as we move along. Ionic compounds are comprised of what we call ions. They're actually charged particles. An example is sodium chloride, NaCl. And these are more complicated. Some ionic compounds dissolve in water and other ones don't. Early in the chapter, at the beginning, we'll assume that if it's an ionic compound, it does dissolve in water, but in fact, some do and some don't, okay? So how do you know something's an ionic compound? Well, strictly speaking, it's when you have ions combined together. So the sodium chloride compound is really a combination of sodium ions. An ion is a charged particle, a charged atom, if you want to think of it that way, or a charged molecule. So you have a sodium ion that's positively charged and a chloride ion that's negatively charged. And I actually overestimated the size of the sodium ion. Let me be a little bit closer in terms of their actual relative sizes. So it looks about like that. So the sodium is positively charged, so we call that a cation. So a cation is positively charged. The chloride ion is an anion, it's negatively charged. And it turns out that ions tend to be able to dissolve into water very well. So ionic compounds, for now, we'll assume that they're soluble in water. They dissolve into water, okay? Now, when they dissolve, they form ions. So the sodium chloride, what it does is the water separates the ions. So now you have a sodium ion and you have a separated chloride ion. Okay. So if we were to put sodium chloride into water, we would have a mixture which is called an aqueous solution. And so in that aqueous solution, we would have water, right? We would have sodium ions, and we would have chloride ions. And those would be the 3 species that are dissolved in that particular solution. A solution is a special type of mixture. It's a mixture where everything is so well dissolved, you cannot see any particles combined in it. Okay? So, generally elements don't dissolve in water. Ionic compounds generally do, and they break up into ions. Okay? Now, how do we know what ions they're? Well, first of all, let's talk about these ionic compounds just for a moment. So ionic compounds. Ionic compounds, generally, they are a metal ion. So a metal ion is positively charged, and they're combined with a non-metal ion. That's the general format. Okay, positive, negative, right? So what you want to do then is you want to remind yourself what are the metals and what are the nonmetals. So in the periodic table, you have the metals. So you have that first column there, right? So lithium, sodium, potassium, rubidium, and cesium. And then you got that second column, beryllium, magnesium, calcium, strontium, and barium. So those are metals, these elements right here. Hydrogen's generally not considered a metal. It's generally considered a non-metal, although it has sort of properties that are in between. Okay. Metals conduct electricity in their elemental form, but they also form positively charged ions. That's the key part to this. That's one of their properties. So if a metal is in this first column, you can tell what its charge will be. It'll be +1. And if it's in the second column, it'll be +2. Okay. So those are metals. Then you've got these metals in the middle, starting with element 21, and it goes all the way to element number 30. So it starts with scandium, and then it ends up with zinc here. So you got zinc, and you got copper, and you got nickel, and you got cobalt, and you got iron, and you got manganese, and you got titanium, and you got vanadium, and you got chromium, right? So those are all what we call transition metals. So those are metals. So they will also form positive ions. Okay, metals will form positive ions. And again, what's a positive ion called? It's called a cation, right? So all of those will form. But there's no real pattern like there is with the first two columns. With the transition metals, it's not easy to say, oh, it's in the first, scandium's +1 and titanium's +2. It doesn't work that way. It's just more complicated. So sometimes we just have to memorize some of them. So a couple that we need to memorize is zinc. So zinc, I'll write this down here. I'll write it up here. Zinc is +2, so we write it as 2+. And then silver is right underneath copper. So silver is +1. And those are the two in the transition metals that you want to memorize. So they form +2 and +1. Then you get to what are called the metalloids and the nonmetals. So metalloids are sort of in between metals and nonmetals. And then the nonmetals are nonmetals, right? So what happens then is you get up here, you have boron, and then you have carbon, and then you have nitrogen, and then you have oxygen, and then you have fluorine, and then you have neon, and then up above here is helium. We're not going to be concerned with these elements because they don't form compounds, so we don't have to worry about those. Are elements, and like I said, elements don't dissolve in water, so we don't need to worry about those. But we do need to worry about some of these over here. So you got boron, and then aluminum, silicon, phosphorus, sulfur, and chlorine. And then I'm just going to do some of these under here: arsenic, and selenium, and then bromine, and then iodine over here. So there's a bunch of elements over here, but we don't need to worry too much about a lot of them. Just some of them are important. So the first thing to say is that the nonmetals, the nonmetals really start over here, like right there. Boron is a metalloid. Silicon technically is a metalloid as well. They're not really nonmetals or metals. Aluminum is a metal, so this is kind of interesting. Aluminum is a metal. sort of in a weird place, but there are metals on the right side of the periodic table as you move down. So that's actually the third one you want to memorize. Aluminum is +3, so I'll write it as 3 plus. So that's this one here, and then those. Those are the three that you want to memorize, okay? So here's what happens. There's a pattern on the right side. So the pattern is -1, -2, -3. Sometimes people will put -4 here, although, to be honest with you, there's not a lot of substances where that actually works out, but you will still see that. So, I'll put this in parentheses to say this is pretty rare that you actually see it, but sometimes you will. So -1, -2, -3. So what that tells us then is that the anions are over here. It's very rare that you'll see a lithium anion, Li negative. So I'm not going to claim it's impossible, but it's pretty rare. You're not going to see scandium negative or -2. They're going to be positive. These are all metals, so they tend to form positive ions, cations. The non-metals are really these ones over here. In fact, the most important ones really are these here. Those are the ones that I wrote out here. And just so you know, this is group 7A, this is group 6A, and this is group 5A. So really we're focused on these ones. And you can tell what their charges are going to be. So like when I wrote that NaCl is Na plus and Cl is Cl minus, well, how did I know that? Well, I knew chlorine was in this column here, so it's -1. And I knew that sodium was in this column, so I knew that it was +1. So that told me right away. If I said iron, that's a little bit more complicated. Iron is right here, ferrum. It's not obvious what that one's going to be. It turns out it could be +2 or it could be +3. It turns out that titanium could be +2 or +4. There's different possibilities when you get into those transition metals. So we generally figure it out from the formula. But here you just know it's +1 and -1. That works out perfectly. Okay. So in general, ions will form when you take an ionic compound. So that's a metal with a nonmetal. And those ions will form in the water. I will spend a moment talking about the whole process of dissolving these things, but I want to go through the third category. So there's the elements are not soluble in water. The ionic compounds generally are soluble in water. The third category are what we would call molecular compounds. Okay, so molecular compounds, how do you know something's a molecular compound? Well, it's all nonmetals. So it might be something like this, NO2. So nitrogen and oxygen are both nonmetals. You might have C6H12O6. Okay, well, you got carbon, hydrogen, and oxygen. Those are all nonmetals. So that's a molecular compound, Another example might be, let's see, CH3OH, right? That's an alcohol right there. So carbon, hydrogen, oxygen, those are nonmetals. So that's a molecular compound. And in general, they do not ionize. So if you put them into the water, they will not form ions, which makes it, in a sense, easy to analyze. You don't have to figure out what the ions are going to be. So you wouldn't see something like this. You wouldn't say NO2 is going to be, N-3 and O-2, No, they don't form ions. The ionic compounds form ions. So molecular compounds, they just dissolve in the water. So if I put C6H12O6 and I put it in water, then the species present, it's just going to be water, right? Because you have the water in there. You're dissolving it into the water. And then you're just going to have C6H12O6. Right? So it may dissolve in the water. Some molecular compounds dissolve in water. This one does. If they have oxygen, they tend to. Some don't really dissolve that well into water, but we don't need to worry about that for right now, the details of which ones do and which ones don't. If it's a molecular compound in general, you're just going to have the water and then the chemical compound for that substance is there. Okay, so let's talk real quick then, before we get into the precipitation reactions, about this idea of hydration. Okay, so you got this idea of hydration. You can see a lot of terms here. You got hydration, you got electrolytes. Okay, so hydration is where water dissolves. substances. So when we say something is hydrated, what we mean is the water has dissolved it. Okay. Hydration really means surrounded by water. It's the process where water surrounds things. But when you dissolve something into water, the water surrounds it. And then electrolytes are ions. These are just ions, right, in water. And they're called electrolytes because they conduct electricity. So, we know that metal wire can conduct electricity, but it turns out that ions dissolved in water can also conduct electricity because they are charged particles and they're capable of moving. An ionic compound actually doesn't conduct electricity very well. They're actually insulators because the ions are locked into place with respect to each other. But when you dissolve them into water, they're now mobile. They can move, so they can carry charge and move the charge around, so they conduct. So we call them electrolytes. Okay, so that terminology is used in health, right? In nutrition, hydration. You got to stay hydrated. What that means is you got to keep water in there so that you can dissolve these electrolytes. And keeping an electrolyte balance is important. So there's at least two aspects. So that one is having enough water to dissolve the electrolytes, and then the other one is making sure that you have enough electrolytes in there to have the electrolytes. Okay. All right. So now let's talk a little bit about this process of hydration. I'm going to do it just with the ionic compound first. So if you take sodium chloride, NaCl, sodium chloride we know is a salt. I mean, it's a solid, right? We call it table salt. As a crystal is called halite. And it's comprised of ions, like I said, but it's not just individual molecules. It's actually, I'm not going to write the symbols in, I'm just going to write the charges. The sodium is positive and the chloride is negative, but just to make it easier to draw. That what happens is when you actually have like this tiny little piece of table salt, it's actually, trillions of these little ions that are attached to each other, right? And so, there's two rows, but it's actually much more than that. It's a gigantic number. And so it's alternating. See how it alternates? You got the plus minus, the plus minus. It turns out sodium chloride forms a simple, what's called a cubic structure. And I'm just drawing, a few rows of it, right? So imagine that this extends out, millions of rows and millions of columns across, and then it is three-dimensional. So it actually, right, it's a cube, right? It's not, it's not like a little plane. It's actually a cube, right? That's just one little granule, right? And it turns out that if you use X-ray diffraction, you can actually like image this thing and show that it's actually like a little cube. It actually forms a little cube. And the little salt particles that you see, or if you actually look at them under they get roughed up on the edges just through the friction and collisions. But if you grow them, if you grow these crystals, they show up like little cubes. And other types of materials, other ionic compounds form different structures. Some of them are not cubes, but that particular one is. Okay. Metals often do that as well. Like actually a piece of metal is actually typically it's like a cube. It's a cube of atoms that are stuck together, but they're not ions, they're just individual atoms. So that's really what you got there. So what happens is the water molecules come along. So imagine you drop this little salt particle in the water. And the water molecules, there's a large number of them. You have to have a huge number of water molecules for this to happen, right? So it's, you got to have a ratio of like 10 or 20 to 1 of water to ions. But if you have that big ratio, what happens essentially is, we'll talk about this more later, but water, let me do it up here. Water is H2O, right? And it has a bent structure. And it turns out this bent structure and this property called electronegativity give the water molecule individual charges. Effectively, the oxygen atom is negatively charged and the hydrogen atoms are equally positively charged. So overall, it's neutral. But you end up with this negative charge. And remember, electricity, opposites attract, right? So this oxygen is attracted to this sodium ion on the corner here. And then what happens is another water, remember it's three-dimensional, so the waters can attack from different angles. Right, so there could be one up above that's actually coming, one below, like all over it. Right? But it turns out if you get enough of these waters, they will actually be able to rip that ion out. Remember, everything's got energy, everything's kind of vibrating and moving around and stuff like that. So, boom, breaks off, right? So then what happens is you get this, little ion here, and it's surrounded by a bunch of water molecules, and the oxygens are pointing towards the ion, right? It's a very active thing, collisions and energies. Pretty complicated stuff, actually. And then again, remember, it's three-dimensional, so there's like one above. But it turns out like this is what we might call like a hydration layer. We've got these water molecules around it. That's not enough to dissolve it. It turns out like to really dissolve a salt, you need like 20 or 30 of these water molecules. So another layer, and I won't draw the structures, but another layer, kind of like an onion, you can get another layer of water molecules out here, and then even a third layer. So a charged ion, an ion has a lot of electrical energy, it turns out. That's part of the reason that life uses ions is because they have so much energy. It's like there's stuff you can do when you have energy, right? If you have energy, you can do things. If you don't have energy, you can't do much. That's why physicists are so afraid of the end of the universe. They're so concerned about that. No usable energy. So anyways, you get these layers. They're called hydration layers, right? So each layer like an onion. Remember, it's three-dimensional, so it's like an onion. And all of those water molecules are sort of, they've got that ion. So the ion is like moving around, but it's dragging all these water molecules. It's like, like a football player that's dragging 3 or 4 tacklers with them, right? Same idea. And then what happens is once that ion's gone, right, it's gotten pulled out. It's a surface phenomenon, right? It's going to happen at the surface. So then what happens is now there's like less attraction for this ion. It doesn't have as many positive charges around it. So it's not held on as tightly. So then more water molecules can come in. And then, but they flip. So they come around like this. Oops, sorry. Got to use the right part of my brain. They flip around like that. Right. So now the hydrogens are attracted, right? The hydrogens are positive, and technically the hydrogens aren't positive, but that's the terminology we'll use. And the oxygen's negative. So now those, again, they're colliding with each other. It's not like it just comes up and sticks there. It comes up and they're bouncing around, and they're pulling and stuff like magnets, right? So eventually that negative ion gets pulled out by the water. And then what you have is this negative ion, and it's got, same as with the cation, it's got all these cool hydrogens. And I'm not drawing the correct number in here. I'm just trying to give you an idea. Good pictures are available online. All right, you'll see I'm not an artist. So they're all attracted. You get a hydration layer, right? And then you have another hydration layer. The innermost hydration layer, I think, has 6 waters in general. So you have kind of like a square. So you got your ion here, you got 1 on each corner. So that's 4. And then you got 1 above coming out, and then you got 1 below coming in. So that's 6. So 6 is a common number for what we call coordination, where 6 waters will coordinate to an ion, or 6 waters will coordinate to a molecule, that kind of thing. It's just geometry, right? Like how many are you going to be able to fit in there if these things are taking up space? 6 generally tends to be the number when you're talking about the geometry of three-dimensional space, right? But that's just one layer, and then there's going to be another layer. Now that layer can have more water, right? Because it's got more, it's further out, so it has more surface area. So instead of having 6, I don't know, it might have 12, and I forget what the numbers are. At some point I knew them, but you end up with like 20 or 30 of these water molecules. And so there are some, there's some cool simulation software you can find where they show you these phenomena, and you'll see like these little ions bouncing around, but dragging all these water molecules around, and they're bouncing around. And that's essentially what happens. So how do we draw that without having to put in like a whole picture of all that? See all the pictures, right? So the way you do that using symbols is very simple. You say, hey, here's our sodium chloride. It's an ionic compound because it has a metal and a nonmetal. It's a solid. We write them as separate ions, and you write AQ after it. Now, this is not really a chemical reaction, although it kind of gets down to an issue of really what is a chemical reaction versus a physical process. But this is how you write it. So this is aqueous. So that means dissolved in water. Right? So these are dissolved in water, right? We write them separately. They're separate ions. So we write the cation, and then you write the anion. Now, I don't think there's really a rule. You got to write the cation and then the anion, but in general, that's the way we do it. Just sort of a convention, okay? Now, to indicate that this went into water, usually what you do is you put water in either above or below the arrow. Okay, so that's an L, sorry, H2OL. Okay, so sodium chloride, which is a solid, is dissolved into water. Water is called the solvent. And then that forms sodium ions and chloride ions, and they're dissolved in the water to put aqueous. Now, these kinds of things can happen in the gas phase, like in the atmosphere. Like you could, in theory, have a sodium chloride particle, a salt particle in the air. It does happen, right? If you're near the ocean, the wind can blow water into the air, right? That's, you can feel its humidity. Sometimes you can taste it or smell it, right? You taste the salt in the air. What happens is once it's in the air, sunlight can evaporate the water off, and you end up with a little tiny little particle of salt. And that's, to some extent, that's kind of how clouds are formed. You have these little crystals in the air, and then water condenses on them, and you form a cloud, right? So you can have it in the gas phase. So you have this sodium chloride, which is a solid, in the gas phase. And then what happens? Well, it can do the same thing. It can break up. It doesn't happen very well, but this would actually be in the gas phase. So that's in the air, right? That's not a very common process. I mean, it happens, but it's not the kind of thing that we're concerned with in this course. We're mainly concerned about, what's happening in a human body, or what's happening in the ocean, or what's happening in a factory. And it's generally not this kind of process where it's gas phase. We're more concerned with what happens in water. Okay. So that's just a little background on hydration. It'll help you with the first Alex problem, which is section 4.1 on the topic is called general properties of aqueous solutions. So I went over that. Okay. So let's take a look at precipitation reactions, because once you get to precipitation reactions, you kind of got something real here. So let's do section 4.2. Okay, so there's two things that Alex is going to have you do. The first is to write what's called the net ionic equation. So I'm going to start with that. This is a skill. How do you write the net ionic equation? And the way these problems are set up is they're going to give you sorry, let me put this over here. They're going to give you an equation, and it's balanced. They're going to balance the equation for you. So here's an example. So notice both of the reactants are aqueous. That means they both dissolve in the water. They put a little space between the coefficient and the symbol. And then notice one of the products is a solid and the other one's aqueous. That's important. This is called a precipitate. A precipitate is a solid that forms in some chemical process. Okay, it's a solid. So that's the precipitate. So anytime a solid is formed in a chemical reaction, we call that the precipitate. So what this tells us is that when you combine these two materials, you get a solid out of it, right? Both of the reactants are aqueous. So, just kind of draw you a little picture here. Essentially what we're saying is you got something that's dissolved in water. Okay, so it's dissolved. Like, like you dissolve sugar in the water, you dissolve salt in the water, it's dissolved in the water. So that's your FeBr3, right? Dissolved in water, okay? Turns out it would be sort of like a reddish color. Then you got this other material, which is also aqueous, and this is the Na3S. This one would be colorless. All right, but you wouldn't see any particles in there. It's not like you'd have a solid in there. Okay. So then what happens is you mix these two together. So you pour this one and you pour this one into another container. So now you have more of it, right? And what's going to happen is you're going to get a solid. So they're telling you that that solid, that precipitate, is Fe2S3. That's an S, solid. Okay. All right. So that's what's happening. And then there's another thing that's going to be up here. This is your aqueous right here. So up there is going to be NaBr. It's also colorless, by the way. Okay. So this is called a precipitation reaction, where you take two things that are aqueous, meaning they dissolve in water, you combine them in the water, right? And then you get a solid out of it. We're mainly concerned about this precipitate here. That's the main thing, okay? And we're going to write the net ionic equation for this reaction, okay? So this can be used for certain things, like there's weight, like, so for example, suppose that I had, water that was coming out of someone's house and it had iron dissolved in the water, right? There's iron, and we want to get the iron out. What you could do is you could combine the water with this compound, which also dissolves in water, and then you get the iron in the form of a solid. So then it's down at the bottom. Then you could just pour your liquid off and you'd have that residue down at the bottom and you could separate that out. So it's a cool kind of thing that we can take advantage of. Precipitation reactions are very common in nature. You find them in biology. So for example, bone formation, right? Bone formation is a precipitation reaction. It's a very complicated one, right? You've got calcium and phosphate, but you also have, proteins and stuff like that, right? So it's, collagen. It's not a simple precipitation reaction, but it is a precipitation reaction. Another one are what they call them kidney stones. If you know anybody that's ever had kidney stones, I had one. I have them. It's like very painful. They can be very painful. So kidney stones, what happens is you got this calcium that's in your diet, right? So you have calcium. And then, in your diet, you have phosphate. So certain foods have phosphate. And what happens is they can combine and you get calcium phosphate. And it's a solid, it's a precipitate. So what happens is they start growing and they don't dissolve very well, right? They just don't dissolve in water very well at all. And so over time they can get stuck, and that's very, very painful. And it's not just calcium phosphate, it's also calcium oxalate. Like I drink a lot of coffee and I eat chocolate and these things, I don't really drink much wine, but certain things that we eat have oxalate. This is called oxalate. Certain vegetables even have oxalate. So what happens is your body just may lose the ability to keep these things dissolved. And so then what you end up with is calcium oxalate. So same thing. It just doesn't dissolve in water. Calcium salts often don't dissolve in water very well. So then you could get a mixture. In fact, if you get the lab work, they will actually sometimes give you a breakdown, what percentage is calcium phosphate and what percentage is calcium oxalate, right? And there's genetic aspect of it as well. So they say if you're prone to these kidney stones, they get stuck and they hurt. If you're prone to those, drink a lot of water, stay hydrated so you can keep these ions dissolved, and you can vary your diet as well. But those are precipitation reactions, formation of a rock in water. Like if you see a rock form in water, that's a precipitation reaction. Seashells, right? So these animals have a way of putting a shell, right? It's kind of like we put together bones, they put together shells. Those shells are precipitation reactions. They're generally over time they become more simple, I think, than bone. There's not collagen and stuff like that as much of it anyways. And then over time, as the animals die, their shells will fall to the bottom of the water. And then over time, they'll get buried with sand, and then they get compressed, and they get turned into limestone, right? So limestone is essentially all these old ancient seashells that have been pressed together by enormous temperatures and um, pressures. And then you got the stone, which is really beautiful stone. Okay, so here's our reaction. What I'm going to do is, I guess I'll just erase this over here. I'm going to show you how to do the net ionic equation. I'm sorry if I sound like I'm rambling a little bit.
Professor,
Mm-hmm.
how about if there is two positive charge?
You know, if they're positively charged, they try to stay away from each other. So they don't tend to do anything. They just stay away.
That means if we have positive and negative, it's always come with solids.
We won't say always, because in the next topic we'll look at how sometimes they don't. So for example, right, see how that one's not a solid? So this is Na plus, and this is Br minus. So they're opposites, but they don't form a solid. So we'll have to deal with that kind of separately. So sometimes they do, sometimes they don't. Okay. But in order to form a solid, it's got to be plus and a minus. We could say that. Okay, so let's take a look at this one. How do you get the net ionic equation? Well, it's a little tricky. You have to know these positions in the periodic table like I talked about earlier. That it's essential, you know, to be able to do these. So let me show you. I'm just going to put them back up here. So here's your column 1A. Okay, so that's your column 1A, and then you got your column 2A. Okay, so column 1A, 2A. Remember we said these are going to be +1, and these ones are going to be +2. All right, so if you look, you know, hey, there's right there, it's a +1, right? That's sodium right there. And, you know, I don't see any others. There's no calcium or anything like that in there. But most of these problems, one of them is going to be over there. And then, you know, there were a few, right? There were a few over here. I said, like, you know, you got to know your aluminum. Aluminum's +3, right? So aluminum is underneath boron. So this one right here, I'll circle it because we said that aluminum's got to be +3. Okay. And then we said then over here, you got this zinc, and that's got to be +2. And then underneath over there was this one over here, which was silver, and Ag is plus. So what happens is there's just certain ones they're going to give you, and they're just very common to chemists. Like chemists often deal with silver, they often deal with zinc, and they often deal with aluminum. So we don't worry about all of them, but there's some that we do worry about. And so first two columns, and then these three here, and then that was it for the metals. Really, like everything else, you're going to have to figure it out from the non-metal. So then we said, if you come over here, you got your fluorine, you got your chlorine, you got your bromine, and your iodine. These are -1. And then next, that's oxygen, sulfur, selenium. This is -2. And then nitrogen and phosphorus were -3. I guess you could put arsenic there. And then those are really the only ones in the periodic table that you're going to need to worry about. All right. So these are the ones that are negative over here on the right, and their position in the table will tell you what their charges are. These ones over on the left, we know what those are. And then we've got 3 here. And then you say, well, wait a minute though. How do you do with iron then? How do you do with that one? What happens is we'll figure that out from the bromine. We can figure out what bromine is, so that will tell us. It's just simple arithmetic. And then, you know, some of them are already in there, like sodium is +1, and here's sulfur. So sulfur is -2. So some of them we know from their position. The ones we don't know from their position in the table, we'll figure it out with the one that they're combined with. Okay, so here's what I'm going to do. I'm going to take this equation, this balanced equation, I'm going to rewrite it. And remember, we have to be able to count things. We have to be able to count. So let's remember we did that back in chapter 3, counting the number of atoms and ions. So when you look at FeBr3, first look to see if it's aqueous, and it is, it's aqueous. That means it will form ions. It'll break up into ions. Now we just have to figure out what those charges are of those ions, and we have to figure out how many there are. So here's how I'm going to do it. You break it up into the metal and the nonmetal, the cation and the anion, and you count. There's 2 irons, so 2Fe. And then remember, the coefficient is everything in the formula. So that's 2 times 3, so you got 6 bromines. Okay. Now you figure out their charges. The bromine is easy. It's right here, so it's -1. That's easy. But what about the iron? We don't have a rule for iron. It turns out iron could be +2 or +3. In this case, it's going to be +3. Here's how you figure it out. You use arithmetic. All these charges have to add up to 0 because it's a compound. Compounds don't have charge. So that means 2 irons plus 6 bromines has to add up to 0. So let me show you the arithmetic for that. I'm going to erase this part up here. I mean, technically it's algebra, right? So you got 2 irons, so 2 irons. We don't know what their charges are. We're trying to figure out. But we do know that the bromine's -1, and there's 6 of them, so 6 times -1, right? So 2 irons, 6 bromines. They got to add up to 0 because it's a compound. So now you're just going to solve for the iron like a variable. In fact, if you want to write it like an algebra, you just write 2x, right? X for each iron. And then 6 times -1 is -6. So I'm just going to write -6. You add 6 to both sides, and then you divide by 2. And you got +3. So now you know the charge. Now remember, in chemistry, you want to write it as, you want to write the number and then the charge up above it. Right? That's just sort of convention rules. So there you go. And you can check it, right? If you have 2 +3s, that's +6. If you have 6 -1s, that's -6. They count it. Then you do the second one. Second one's easier because we have sodium is plus and sulfur is -2. We already have them. We don't have to figure out one from the other. So now how many are there? There's 3 times 2 sodiums, right? Remember, there's a subscript too. So 3 times 2 is 6. And then how many sulfurs? 3 times 1, so 3s. And again, the charge there is 2-. And you can check, again, that's going to add up to 0. 6 positive 1s, 3 negative 2s, that's +6 and -6, they counter. Now see how much room it's taking? I'm going to show you, it actually takes up a lot of room. Next thing you do, okay, so you've broken up both of the reactants into separate ions. So there's 4 different reactants, not 2, but 4. So even though we would say, hey, it's iron bromide, that's the reactant, it's really iron 3 and bromide. There's really 2 reactants in that iron bromide, 2 substances. Now, because I've run out of room, I'm just going to write it underneath. Now, see how it says solid? That means it doesn't break up. That's what the solid means. It means that it stays intact. So you don't break up the ones that are solid. We'll see in acid bases, you don't break up liquids either. You only break up the ones that say aqueous. Okay. So the last one is aqueous. So there's 6 sodium bromides. So sodium's +1 and bromide is -1. How did I get those? Again, well, they're not different from on the left side, but the bromide is here. That's -1. And then the sodium is over here. That's +1. How many are there? Well, it looks like there's 6 sodiums and 6 bromides. So 6 and 6. Okay. That right there is called the ionic equation. And you want to put the states of matter in. The way you put the states of matter in is very simple. If it's an ion, if it has a charge, you put aqueous. Anything that has a charge, you put aqueous, and these all have charges. So aqueous, 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 and then aqueous. Okay, that's called the ionic equation. But that's not what the question is. The question is, what is the net ionic equation? What's the net ionic equation? Well, the net ionic equation is like, it's sort of like, if if someone gives you $100, but then you give 50 back, the net change is 50, right? 100 minus 50. So you're going to subtract out everything that's the same, you know? So here's how you do this. Anything, you remember in algebra, if you had x plus 3y plus 2 equals 4x plus 2, if you had the same thing on both sides, you could just subtract them. You could just cancel them. You can do the same thing in a chemical equation. So anything that's exactly the same on both sides, you can cancel them. So if you look at it, you've got 6 bromides aqueous, so they cancel. And then you get 6 sodiums aqueous, you can cancel both of those. So what does that leave with you? Now your net, just like I would do this, I would just say now this is x plus 3y equals 4x. Same thing here. You have, I'm going to write a line under here just so that we know this is our new equation. This one's going to be shorter because we've canceled things. So now you're going to have 2Fe3 plus aqueous. Notice I'm putting the states of matter in again. Plus 3S2 minus aqueous goes to Fe2S3. Solid. And then that's it, right? We're done. There's nothing left. Everything else has been canceled. This is called the net ionic equation. Okay, that's the net ionic equation. Net meaning we've canceled out everything that's the same on both sides. Terminology. You'll see this if you have to go on and take exams in, like if you're going to take the PCAT or the MCAT, any of those kinds of professional exams. The net ionic equation, what we've done is we've canceled out what are called the spectator ions. So the things that got canceled, so sodium, that got canceled, right? And then the bromide got canceled. Those are called spectator ions, which is a cool name. It just means they were spectating, meaning they were not involved in forming the solid. They were just in the solution. So they're spectators. Okay. The net ionic equation should be balanced. Let's check it. 2 irons, 2 irons, 3 sulfurs, 3 sulfurs. The states of matter should be written in. And remember, for a net ionic equation, if you have a net ionic equation, one of them, the product will be solid. So it's aqueous plus aqueous gives you solid. And let's see. And if they're ions, you got to write the charges in. So a common mistake is people will just write 2Fe. That's no good. You can't just write 2Fe. That would mean you have a piece of iron metal. If there's no charge on it, iron is a solid. You build bridges and nails out of it, right? We're talking about ions dissolved in water. So this is Fe plus 3 or Fe3 plus, okay? So you got an ion, you got an ion, and the form is you get a compound. The compound has a charge of 0, and that's your net ionic equation, okay? I'm going to show you another example because there's a lot of steps in that one. Okay. Should I show you this one? Let me see. I'm going to show you 2 more, actually, because some of them require polyatomic ions. Actually, most of them are polyatomic ions. Here's one that's not, but I'll do another one that has polyatomic ions. AgF, KBr, AgBr solid. See the form? Aqueous plus aqueous gives you solid plus aqueous. That's the form of these. And we're going to write the net ionic equation. That's the question, is just to write the net ionic equation. Okay? Okay, so let's go through it. Remember, the logic is if it's aqueous, you break it up into 2 separate ions. All right, and you separate them all by plus signs. Plus means different. It means that you're adding a different thing. Okay, so both of those are aqueous. So now you're going to have 4 things, right? And then on the product side, you're only going to have 1 here. Why? Solid. So if it's a solid, you don't break it up. And then this is aqueous, so you can have 2 things here. All right, 1, the metal and the non-metal. Most of these are pretty simple. They're the ones that I told you to know. So silver was one I said to know, +1. So Ag plus. Fluorine is in group 7A, so that's F minus. This one is balanced, by the way, so we don't have to worry about like the 2s and the 3s and the 6s and all that. This one's balanced with 1 to 1. K was in group 1A, and then bromine is in group 7A. So we got your charges. So it's K plus and Br minus. This one's a solid, so you just write it down. And then this one's K is in group 1A, so it's K plus. Fluorine is in group 7A, so it's F minus. So now you get your charges. If it's an ion, you put aqueous. Okay, so anything that's charged, you put aqueous. Ions dissolve in water. This one's a solid. Remember, if it's a solid, it doesn't dissolve in water. So some ionic compounds dissolve in water, other do not. In this one, it's telling you that AgBr does not dissolve in water. That's what the information is giving you. So there's your ionic equation. By the way, if you're Googling this, sometimes people call it the complete ionic, or they'll call it the total ionic, right? Like all the ions that are in this reaction. To get to the net ionic equation, you just cancel everything that's on the same on both sides, exactly the same, meaning same symbol, same charge, same state of matter, okay? So the silver, you can't cancel because it's in a different form on both sides. The fluorine, you can cancel, it looks like, because the fluorine is F minus on both sides. So this one you can cancel. The K plus is the same on both sides. The bromine is not, bromide is not. Bromide is in the form of AgBr on the right, and it's Br minus on the left, so you can't cancel it. So what do you have left? You got your Ag plus. Make sure you put your state of matter, Br minus. By the way, when you write these in, it's considered good form to do the metal first, and then the non-metal. And then you get your AgBr. Okay. That's your net ionic equation. This one was easier to balance because it was already balanced. I mean, everything was a 1. The coefficients were all 1. And then your spectator ions are the ones you canceled. So that would be the F minus and the K plus. Okay, so it's really a simplified equation. All we've done is we said, hey, oh yeah, we had to put these 4 different materials in the water. But what was the actual reaction? What actually precipitated? The precipitate was the silver and bromide. So what that tells you is that you don't actually have to have potassium in there. It could be something else. You could have put sodium in there instead of potassium. You didn't have to have fluoride in there. You could have had something else like, I'm not going to go through it. It could have been some other ion, acetate or something like that. So in other words, really the key ingredients here for the reaction are these 2. If you combine silver with bromide, that will give you silver bromide. That's the real reaction. So to represent the actual precipitate formation, we use the net ionic equation because it's simpler. I mean, look how messy this is, right? That's a lot of stuff in there. And some of it you don't really need to know because, these are the 2 you need to know, right? And again, just reminder, some of those ions that you may not have remembered, right? So one of them was the aluminum, that's +3. Just so you know, if they have actually a cool position in the table. This is element 13. Below and 1 to the left is where zinc is. That's cool, right? And this one's +2. And then below and to the left of that one is 47, which is silver. And this one's +1, right? So there's a kind of a cool, you look for these things, right? We look for these things in sciences. We look for patterns, right? So, there's nothing particular. I don't think there's anything particularly insightful about this. There is a relationship between charges and electrons and position in the table. But this is one pattern that pops up. It would be nice if there were more patterns, actually, but this is one pattern that pops up. Aluminum, AZA, right? If you want to remember it that way, AZA. You got 13, 30, 47, right? And so, and actually, that is kind of an interesting pattern. It goes from 13 to 30, which is a difference of 17. And then it goes 30 to 47, which is another difference of 17. And then it goes to +1. So maybe there is something to that. Okay. So those are ones you just got to memorize. So you want to memorize the group 1A, group 2A, and then your group 7A, your 6A, your 5A, and then these three. And that should do it for most of them. Okay. Now, there is a slight variation to this type of problem. The variation is using polyatomic ions. And we cannot ignore polyatomic ions because they're very important in nature. So for those of you that are biology majors, you're aware that you have this ion called the phosphate ion, and it's a very important ion, right? There's another important biological ion called the carbonate ion. That's that one right there, right? And so there's a bunch of these. This one's not quite as important biologically, but it is important chemically. This is called the nitrate ion, NO3 minus. And this one here is called the sulfate ion. That's called the sulfate. So there's a bunch of these ions that are polyatomic, right? Polyatomic ions are cool. They are essentially clusters of atoms, and they tend to be nonmetals. Most of them are just all nonmetals, but the whole thing has a charge. Okay, this is called the phosphate ion. Right? So phosphate's important, right? If those of you that do your anatomy and physiology and your glycolysis and all that kind of stuff, the phosphate ion, right? So there's your phosphate ion. The carbonate ion, kind of similar thing. It's got this carbon with 3 oxygens. And what's interesting about them is that they act as individual particles. So they act just like, like a sulfide ion, right? So this one right here, it's not all that different from this. It actually behaves just like a one atom with an ion, right? This one right here kind of behaves like a phosphide ion, right? So this is called phosphide. If it ends in IDE, most likely it's just one atom. So this is sulfide. For those of you in other parts of the world, we'll do pH, right? Sulfide. So yeah, in the US, we do phosphorus pH, but we don't do sulfur pH. Who knows why, right? So anyways, these are called polyatomic ions, and there's a bunch of them out there. There's one that's positively charged. Not a lot are positively charged, interestingly enough. This one right here is called ammonium. So the ammonium ion is positive. There's 4 hydrogens. And the whole thing is +1, right? And so, there's not a whole lot of rhyme or reason. There's not a whole lot of patterns to this. We kind of look for them. If it ends in ITE, it has fewer oxygens than if it ends in ATE. Notice a lot of these, they have oxygens in them, right? The surrounding atoms are oxygens. So if it ends in ATE, it has more oxygens. If it ends in IT, it has fewer oxygens, So there's that. But essentially, these are polyatomic ions, and they're going to appear in your chemical formulas, right? They're going to appear like NaNO3, right? Well, that's telling you it's NO3, right? You're going to have, K2SO4. Oh, there's the SO4. That's that one right there. You're going to have your NH4NO3. Oh, wow, NH4. So that's that one right there. And then there's an NO3 too, right? So that one's actually got 2 polyatomic ions. But they break up as ions, right? So, NH4NO3, when you put it into water, it breaks up into ions just like this, polyatomic ions. So the atoms don't disassociate from each other, right? This nitrogen stays stuck with the hydrogens. When we get into chemical bonding in chapter 8, Lewis structures, we'll see why that's the case. Like, why doesn't the hydrogen just pop off the nitrogen? Why doesn't the oxygen just pop off the nitrogen? turns out that they're attracted to each other through covalent bonding. And so the nitrate ion is more stable than separate, separate ions, right? This is not what happens. So what do? We tend to memorize them, or at least have a list. So I'm going to write a short list here. I'm not claiming these are all of them. But I'm going to put a list here. So that's the carbon. So let's do here's another one, CN minus. That's an odd one. That one's actually called cyanide. So it actually ends in IDE, but it's a polyatomic ion. So sometimes that happens. Here's one, OH minus. This one also ends in IDE. It's called hydroxide. So a couple of them, it's just historical. Someone came up with the name before they had the rules of naming. And so, it just happens. So SO4, SO3, phosphate. I gave you that one, right? Phosphate, sulfate, sulfite. You can also have these hydrogen phosphates. Yeah, so sometimes you'll see these ones. Every time you add a hydrogen, the charge goes down by 1, right? Less negative by 1. So those are some of them. The ammonium, right? Oh, I already did the ammonium up there. Any others? There's a bunch, but those are probably the most common ones. Let me see if there's any more that Alex has you do that are different. I'm just going to run through a few Alex problems here and see if any of them are different. OH, I gave you that one. All right. NH4, NO3. Yeah, I think that's most of them. So they're not having you do exotic ions. They're not going to give you like permanganate or anything like that. I would think actually, I'll put permanganate in here. This is an interesting one because it has a metal in it. But, here's another one. Some of them do have metals. Back when I was taking chemistry, they'd say, hey, you got to memorize all 50 of these. And I was never very good at memorizing. So for that reason, I don't make people memorize very much. It's actually useful to memorize stuff, though. For those of you who've taken anatomy and physiology, if you can't memorize stuff, you're going to fail. Okay, so let's take a look at an example. So we're just doing the same problem. It's just this one's going to have the polyatomic ions. Okay, that's the only difference here. So let's take a look here. So in this one, they're going to give you, so the disadvantage of the polyatomic ions is they take up more room. So I'm going to try to write this small. So see how, it's the same pattern, right? Both reactants are aqueous. That's how these problems are set up. And then one of them is a solid on the product side. Now, textbooks will often give you like one, you have to do one where both the products are aqueous. So then what happens is if they're both aqueous, everything's a spectator ion and there's no reaction. But that's just a way of saying there's no reaction. So I don't see that Alex is having you do that though. Okay, so there's your balanced equation. And it does, there's a 2 in there. Actually, there's only 1 2 in there, but there's a 2 in there. So, keep those coefficients in mind. That's going to give you the numbers, right? So look at this one. There's actually 2 polyatomic ions, right? You've got the nitrate, NO3. So NO3 is NO3 minus. And then you got your NH4, which is really NH4 plus. The zinc is one of the 3 metals I said to memorize. It's +2. And the sulfur is in group 6A, right? That's here, sulfide, we would call it. That's in group 6A, which is sometimes written as group 16. So be careful when you're looking at the periodic table. So like the newer version of the periodic table got rid of the A's and the B's, which is kind of a shame because the A's and B's are easier to remember. 6A means 6. But they switched it to 1 through 18. So that means it's in group 16. But you can just take a periodic table and write them in up above. Okay, so zinc nitrate, ammonium sulfide, zinc sulfide, which is the precipitate, and then you got ammonium nitrate. Just be aware of the numbers. So first we do the ionic equation, right? The total ionic or the complete ionic, right? So remember, think of them as two parts. Often we call these binary ionic compounds. Remember, binary is 1010. So this binary means there's two parts, the metal, the non-metal, or the cation and the anion, right? We're not dealing with these gigantic, complicated compounds. These are just simple binary ionic compounds. So you got your zinc. Looks like there's just one. And then you got your nitrate. Looks like there's two, right? Is the parentheses with the two. What are the charges? Well, zinc, again, that's one we needed to memorize. And then the nitrate, that's this polyatomic ion here. All right. What I would do is I would just write all these on a card and have them next to me. And then I'll write the states of matter underneath, right? So anything that's charged is aqueous. Okay. Then you have two of the ammoniums. So remember, you got to put that two out in the front. People often forget that. The charge is up here. And again, I'll write this underneath. Plus sulfur. Sulfur's in group 6A, so it's 2 minus. All right. I'm just writing the states of matter underneath because there's not enough room to write everything up on this. If I had switched the iPad to landscape mode, then I could have fit it in there. But then you can't fit as many rows. Okay, there's your solid, right? So you just bring it straight down. The solid, you do not break up into ions. And then now be careful with this. You got a 2 in the front, right? The 2 refers to everything that comes after it in that compound. So you've got 2 of the ammonias. All right, there's your ammonia. Ammonium, I-U-M. And then you've also got 2 of the nitrates. Now, if you want to say, like, what, I don't see why that's 2. Come back over here. It's got to be balanced, right? See how we had 2 of the nitrates over there and 2 of the ammonia? So it has to be 2, right? But the point is that the coefficient in front of a chemical formula refers to everything that comes after it in the chemical formula, right? And so aqueous and aqueous. So with this one, we can cancel out, remember, that's the ionic. We can cancel out everything that's the same on both sides. So we can cancel the nitrates and we can cancel the ammonium. So certain ions always get canceled, interestingly enough. Ammonium always gets canceled. Nitrate always gets canceled. In this list, those are the only 2 that always get canceled. But there is one more, which, I feel bad that I didn't put it up here. It's called acetate. So C2H3O2 minus. This one also gets canceled always. And acetate can also be written as CH3COO minus. So sometimes it's written that way as well. Okay, C2H3O2 minus. Okay, we canceled everything. Remember, the ones that get canceled are called the spectator ions. So then you just bring down whatever is left over. Now we have room, right? Once you get everything canceled, that will cancel. Now you've got room. And now we can be very sharp and to the point. Zinc sulfide is our precipitate. And then that's it, right? There's no plus there. That's it. That's your net ionic equation right there. So actually, interestingly enough, the polyatomic ions got canceled, right? So in this particular example, even though we had polyatomic ions as spectator ions, the ammonium and the nitrate are the spectator ions, they did not appear, the spectator ions do not appear in the net ionic equation. So this one is sulfide. Sulfide, actually, it turns out sulfide precipitates almost everything. And I'm going to look at that. We only have about 15 minutes left, but I'm going to look at that in the next Alex problem, which is predicting the products of precipitation. Okay. So there you go. All right. So I think I did like 3 or 4 examples there, right? At least 3. One with polyatomic ions. So these are the common, I just went through the Alex and I didn't, it doesn't look like they gave you any more exotic polyatomic ions. So some of them are with the polyatomics. Some are just with the regular elements like, zinc and silver and sulfide, but it looks like some of them are polyatomic ions. So you need to be able to do that one. And there you go. So this is, in a way, it's a little simplified because they're actually balancing it for you. If they didn't balance it for you and you had to do that, that'd be an extra step. They're giving you the states of matter. Like a lot of times we expect people to figure out the states of matter using the solubility guidelines, which I'm going to go over in the next example. Okay. And there you go. So that, I find that that's one of the trickier problems for most people, because if you look at it, you know, I mean, that was the third or fourth one I did. I did it pretty quickly, that last one, but you know, there's a lot in that, right? You have to remember the ions, and you have to know their position in the table, and you have to know the polyatomic ions, and then, you know, go through the arithmetic and all of that. Okay. So let's take a look at the last one from this section, because I want to make sure that we cover precipitation reactions completely. So this is still section 4.2. Okay, precipitation. But the second type of problem is kind of cool. I like this one. What they do is they give you two solutions. Right? So, you know, when they say a solution, just think like a little cup with some stuff in it, right? And the first, and solution means it's dissolved in water. Okay, and then they give you a second solution, solution B. And then they ask you, are you going to get a precipitate? PPT means precipitate. So when you mix solution A and B, are you going to get a precipitate? And then if you are going to get one, then they want you to write the empirical formula of the compound. Oh, I'm sorry, of the precipitate. Okay, so what's the chemical formula of the precipitate? Right, which is what we just did in the previous example, right? We were writing the one that was a solid, that's the empirical formula of that compound. So first one, I'm going to have to write it with two levels here. So potassium chloride, lead 2 nitrate, and then it's either yes or no. And then you can write the chemical formula. So there's the first one, okay? And then there's two more. You have to do two of them. So let me write the second one down. Actually, I'll write the second one down. We can do it. Second one's ammonium sulfide. And copper 2 nitrate. Here, I'll put a pH. Okay, same idea, yes or no. And then if it's a yes, and if it's a no, there's no formula, right? But if it's a yes, write it down. Last one is copper 1 nitrate. And potassium hydroxide. Okay, now you can't really answer these unless you have what are called the solubility guidelines, okay? So let me save this to photos because I don't want to lose it. And then I'm going to do a new one. So these are called the solubility guidelines. Okay. Now in your textbook, it's table 4.2 and 4.3. There's two tables that are given. Alex also has solubility guidelines, right? So you can use the Alex solubility guidelines as well. Okay. Actually, if I come back and look at that problem, is it allow me access? It doesn't allow me access to it. Okay, that's fine now. I'm going to go with the solubility. So let me give you the solubility guidelines. These are going to tell you whether something is soluble or not. It's just a list of what things are soluble, but it's usually done in such a way that you have to kind of interpret it, right? So here's what it says. If you have an ionic compound and it has a group 1 metal. Now, what are the group 1 metals? Li, Na, K, Rb and Cs. Now they usually include in this ammonium. Even though ammonium is not a group 1 metal, it's a polyatomic ion, it behaves a lot like the group 1 metals. Then it's always soluble. Okay? So that right there is going to get you a lot of them. A lot of them are going to have, like the third one had potassium. So that one right there tells you whether it's soluble or not. Okay? Now, that's one group. Another group are these polyatomic ions. NO3 minus, which is nitrate. CH3COO minus, which is acetate. And is it just those two? Yeah, nitrate and acetate, right? So these ones are always soluble. Now, when we say something is always soluble, what that means really is that you can't form a precipitate from it. So if it has that ion, it will not be a precipitate because it just is always soluble. It always dissolves, right? So the goal of this problem is to find the precipitate. And I'm going to show you how to do that, but you got to have this list here. So then it gets more complicated. What happens is, then the next one is you have this group 7A. So this is group 7A. It's not all of A. It's not all of 7A. It's just three of them: chloride, bromide, and iodide. Just those three. So not fluoride. Fluoride has its own chemistry. It behaves differently. So these ones are usually soluble. So I'm going to write soluble except with chloride, bromide, or iodide. Then they're insoluble. Okay? So in other words, if you have sodium chloride, it's soluble. If you have potassium bromide, it's soluble. If you have calcium iodide, it's soluble. But, I'm sorry. I wrote these twice. Ag plus. Hg2, 2 plus, and Pp. I don't know why I did that. I'm tired today. Sorry. So this is lead 2, this is mercury 1, and this is silver. Okay. So the chloride, so sodium chloride would be soluble. Calcium iodide would be soluble. So they're usually soluble, except with these three metals. So if you had silver iodide, now it becomes insoluble. If you had lead bromide, now it becomes insoluble. Okay. So notice there's some exceptions with that one. So a lot of them have exceptions is the issue. So here's another example. Sulfides, which is S2 minus, it's insoluble. And then you have exceptions, except with Li plus, Na plus, K plus, Rb plus, Cs plus, and NH4 plus. So notice what happens is sulfides are insoluble, except if you combine it with this. If you combine them with this, then they're soluble. But that is logically consistent because if you think about it, I said that these metals are always soluble. So I can't say they're always soluble and then say they're not soluble, right? So, those metals up there are always soluble. So even if you take sulfide, if you take sulfide, which is generally insoluble, you combine it with one of these, it will be soluble. But if it's not with one of those, if it's with iron, if it's with copper, if it's with calcium, it'll be insoluble. Okay. Next one is the hydroxide. Now, I'm not going to go over all of them because they're all in table 4.2 and 4.3, 4.2 and 4.3, and they're also in Alex, so you can refer to those tables. But I wanted to go over some of them. So hydroxide, OH minus. So these ones, strangely enough, they're generally insoluble. So most of the time they don't dissolve in water, except, again, those same ones, Li plus, oops, sorry. Li plus, Na plus, K plus, Rb plus, Cs plus, NH4 plus. But this one has even more exceptions. It's also Ca, Sr, and Ba. Okay. So this one has more exceptions, right? So it's actually got even more. Okay. So let me save this one. Again, this is not all of them, but it's a bunch of them. Okay. These are probably, these are probably the most important ones, to be honest with you. Sulfate, we would want to do sulfate. If I had more time, I would do more sulfate. But we got the nitrate, we got the hydroxide, we got the sulfide, we're in the chloride, we're set. Okay. So let's come back over here. So, all I'm going to be referring to that. So here's how you go about it. Let's do the first one. Potassium chloride. Potassium is in group 1A, so it's K plus. Chloride is in group 7A, so it's Cl minus. So see how they have the same amount of charge, +1, -1? So that means it's just written as KCl. Okay. Solution B is lead 2. Ooh, lead 2. And then nitrate. Okay, so that's your second. That's your solution B. How do you combine them? If one of them has a charge of 2 and the other one has a charge of -1, you got to have a ratio. The charges have to cancel. So that means you need 2 of the nitrates. Okay, 2-to-1 ratio. -2, +2. That's the key. So now, how do we figure out whether you're going to get a precipitate? This is what you do. You take the first part here, the potassium, and you combine it with the second part there. Okay, so metal, non-metal. They're switching partners. Metal, non-metal. So those two are going to go together, right? You're switching partners. Okay. So what you get then is you get the K plus with the NO3 minus. So you get KNO3. You get the Pb plus 2 with the chloride. PbCl2. Why PbCl2? Because the Pb is +2 and the Cl is -1, so you need 2 of the chlorides. Now you go to your solubility guidelines. Always soluble. For 2 reasons. Potassium is in group 1A, so it's always soluble. No exceptions. Nitrate is one of those polyatomic ions, always soluble. So this one's aqueous. So that is not a precipitate. All right, that one is not going to be a precipitate. What about the PbCl2? Well, we had the rule that chlorides are generally the 7A, so usually soluble, except with Pb plus 2, Ag plus, and Hg2, 2 plus. There's your exception, which means it's insoluble. So the answer is yes. We have something that's insoluble, which means it's a precipitate. So what's the formula? PbCl2. Okay. I wrote it in the wrong place, sorry. Let's try the second one. The second one is ammonium sulfide. So let me erase all of this. Well, actually, do I have enough room? Nope, I don't have enough room. You know what? Let me just do this. So I'm going to, let me erase it. I was going to go to another slide, but then there's no perfect solution here. There's no perfect answer to this. The second iPad would be better, maybe. Okay, let's try the second one. I'm going to try to go a little bit slower here. We got ammonium sulfide. So ammonium is NH4 plus. Sulfide is your S2 minus. All right, that's sulfide, group 6A. So that means you have a positive and you have 2 negatives. So you got to have 2 positives. So the way you do that is you have NH42. Remember, you put the cation first and then you put the anion, right? So 2 positives, 1 negative, 2, that balances, okay? Let's go ahead and just do the solubility. Well, actually, we don't want to do the solubility guidelines. We want to do the solubility guidelines of the products. So the second one is copper and nitrate. So copper 2, remember the 2 means it's +2. So copper 2 and nitrate, NO3 minus. 2 positives, 1 negative. So Cu NO3 2. Okay, so there's your 2 reactants. Switch partners. So you take this one here and you combine it. The positive combines with the negative. So remember, this one's +1 and this one's -1. So they're going to give you 1 to 1. Okay, that's the empirical formula. Now you could say, look, there's going to be 2 of them. That's fine. You can put a 2 in front of it, but that doesn't change the formula. That just changes how many there are. Then you take your metal and you combine that with a non-metal. So these two, switching partners. This is often referred to as a double displacement reaction or double replacement. I'll show you what that means in a second. So you got your copper, which is +2, and you got your sulfide, which is -2. So if they have the same charge, the empirical formula is just 1 to 1, okay? Now you go to your solubility guidelines. The solubility guidelines say that nitrates are always soluble, ammonium is always soluble, so this is aqueous. So that means this is not a precipitate, spectator ions. But there's one about sulfide, and the one about sulfide said sulfides are precipitates. They're insoluble unless they're with lithium, potassium, sodium, rubidium, cesium, and ammonium. But this is copper. It's not one of those. So that means it's a precipitate. So there you go. There's your precipitate. Okay, we got one more. Last one. And oh, I circled the wrong one. Sorry. So the answer is yes. And the answer is yes. Okay. Now let's see what this one. This one is, yeah, this one's going to form a precipitate. But let's take a look. I'll just do that down here. Your third one. Okay. Copper 1. So notice that's copper 1. So it's Cu plus and then nitrate. So they have the same amount of charge. They each have a magnitude of 1. So they just combine in a 1-to-1 ratio. Okay. And then you've got your copper 2. I'm sorry, potassium hydroxide. So potassium is K plus. Hydroxide is one of the polyatomic ions, -1. Same amount of charge. They each have a magnitude of 1, so it's KOH. Okay. Switch partners. Metal goes with non-metal. Metal goes with non-metal. So these two go to each other. Okay. All right, so what do you got? You got your copper with your hydroxide. Copper's +1. Hydroxide's -1. Oh, that's perfect. Okay, 1 to 1. And then you got your K and your NO3, both 1. All right, 1 to 1. Now, solubility guidelines. Copper hydroxide. There is a rule about hydroxide. Insoluble, meaning a precipitate. Remember, insoluble means precipitate. Unless you're with lithium, sodium, potassium, rubidium, cesium, or ammonium. But this is not one of those ions. Copper is a different ion, so there's your solid. Now, is there a possibility that both products could be precipitate? It is possible. There are some reactions where both of them are, but it's pretty rare. So let's check. Potassium, oh no, this is a group 1A, never forming a precipitate. Nitrate, never forming a precipitate. So that one's aqueous. So that one we don't have to worry about. So there you go. The answer is yes. Copper hydroxide is your precipitate. Okay. So like I said, this is what we call a double replacement. So double replacement is, imagine it this way. You've got your cation, which is typically a metal, with your non-metal, right? So there's your first reactant. Typically it's aqueous. Then you got your second metal. So I'm going to write it N for your, oh, actually I shouldn't write N because then you might think non-metal. Okay. So here's your, I'll write it M1. So this is your metal 1. And then this is, we'll call this X1, non-metal 1. Okay. So metal 1 and non-metal 1. Now you got a second metal, M2. And then you got a second nonmetal, X2. Okay. A double displacement is this. The metal or the cation, because it's not always a metal, right? Ammonium is not a metal. That one will combine with this one. So I'll write those as, I'll box them off. Those two combine with each other. Okay. So an example of this would be like A, should I do AG? NaCl, right? So here your M1 would be Na plus. And then I'm going to react that with this other one. So you get M1X2 plus, I'll circle these ones, M2X1, right? They're switching partners. And so an example of this might be like sodium chloride plus silver, I guess I'll do silver nitrate. Okay. So what happens is this, the sodium goes with the nitrate. So those two go to there. So you get NaNO3. And then you get the silver with the chloride. AgCl. And then once you've got those, then it's just a matter. So that's called double replacement or double displacement. Precipitation reactions follow that dynamic. So do acid-base reactions often. So we'll look at that tomorrow. Then it's just a matter of using the solubility guidelines. Solubility guidelines say that sodium salts are always aqueous. Solubility guidelines say that chlorides are generally aqueous unless they're with silver, mercury, or lead. Well, there's silver, so there's your precipitate. Okay, so you take, solution A, you take solution B. There's no solid in either of them, right? Both of these are aqueous. You combine them into a container, and you get a precipitate. Usually precipitates are more dense than water, so they go to the bottom. You can use a centrifuge to speed that up. Okay, so there's your precipitate, and then there's your aqueous. So this is where the spectator ions are going to be, right? So your spectator ions like sodium and nitrate, they're going to be dissolved in the water. And then down here is where your precipitate is. There's your HAC. Okay. So there you go. So that's a tricky one, right? That's a lot of work. So it all kind of builds on what we talked about in the previous section. So that's 4.2. 4.2, we did that. So tomorrow, I'm sorry, not tomorrow, Wednesday, we're going to do acid base on Wednesday. And then we'll start, acid base is quick. We just have a few things to talk about with that one. And then we'll go into redox reactions. So we'll do that on Wednesday. And then Thursday, we'll do concentration. Okay. And then, for those of you that have the lab on campus, you'll be in there doing, we're going to actually do the, in the lab, calibration of volumetric glassware tomorrow. And then for those of you that are doing, if you're in section A is the one you're doing it off campus. So you're going to be working on your second experiment, which is, it's not copper oxide, right? It's either copper oxide or titration. I can't remember which one you guys are doing, but one of those two. Okay. So I'll upload this and have a great day, you guys. Have a great day, great week.
Thank you so much.
Absolutely. Take care.